Welcome to lecture number 5 of module 6, and this is in last lecture also we were discussing about the transient stability analysis, and we saw the various approaches and various the models levels for which the AC/DC stability analysis are done. In this we will see in this lecture mostly I will go for the various component modelings, and then we will see what were the methods to analyze, means what are the various methods to solve this transient stability analysis. To see this any practical transient stability program, whether it is for AC or it is a DC or it is a AC/DC both, we have to include the various components that those are involved for the transient stability, and that may include the detailed model of generator considering the flux decay dynamics. Generally third or fourth order models are used. However, in the previous lecture we saw the classical models, only the second order, means you see the second order differential equation, that was the single equation just I derived and I show it, and that is you can see this that is called the second order. But if you are going for the field decay model and taking care of some other components, then we can increase the order of modeling, but as you know the number of differential equations are increasing at the same time. What we are just number of computational burdens for, because it is we are going to increase for each and every machine. So, if you are in power system or whole AC/DC system, you are having n number of buses. So, you are keep on increasing the differential equations and the solution techniques requiring more and more computational time. So, the detailed modeling again up to what label you are going to analyze it. So, that modeling is required. Second, then we have to represent the excitation system, because each generator is equipped with the excitation system. So, that modeling is also to be done. Then, since speed governing system, whether it is a hydro or it is your thermal power stations or even whatever the gas power stations, we are having the speed governing system, and that modeling is to be also included. Then we have to another side on the power system side, especially for the load side, we should also model the dynamic models, because we are having some of the huge induction motors. Also some, even though some of the loads they are dependent on the voltage frequency, those should be also modeled in this transient stability program. Last but not least, if you are having any FACTS devices, including your TCSC static var compensator, that is SVC, or you are having the HVDC systems, those controllers should be also modeled in the transient stability program, because they are also going to affect the stability of the system by its control action. So, whatever other controllers, including your SVC, HVDC and others are there, that should be the model in the detail. So, we will see all these modelings one by one, and then finally, we will just combine together. So, first I will discuss about dynamic model of synchronous generators. As we know, most of the conventional power stations are running by this synchronous generators, sometimes we also call alternators, and they are rotating at synchronous speed, and the synchronous speed, as you know, this is what is the rotating speed, the maximum speed for 50 hertz cycle or 50 hertz frequency, it is a 3000 rpm, especially those are used for the thermal power stations, but for hydro it may be the less, because you know the efficiency of hydro power stations are less at the lesser speed. However, it is a reverse is true for the turbo alternators. So, we have to the dynamic model of the generator include its mechanical dynamics, we have to also include its flux decay dynamics, excitation system dynamics, governor turbine systems, and the detailed modeling should include the air gap saturation also, because always we work on the knee curve whenever the loading is increasing, the saturation is taking place, and the field current limits should be also included, and sometimes we are having some sort of a line drop compensation techniques in our excitation system, that should be also taken care. So, in the previous swing equation, if you remember what I did this equation, if you will see, this is the differential equation, this is the second order differential equation, this is the model, this mechanical dynamics I can say this is a second order swing equation. Here this one term extra this is added, that is a d del delta upon dt, this the dynamic terms was ignored in the swing equation. But since the power system is having some dynamics, some damping factor, and that factor should be also included. This factor basically related with, if suppose you are changing a frequency of the system changes, the net load released by the power system is also going to affect the factor. So, this should be also taken into account, and your right hand side you can say this is the mechanical power minus your electrical power, that is a PG, and this is nothing but is a factor of your delta, that is the machine internal angle, this is the voltage of the bus, and this is a theta is basically angle of this Y bus matrix, that is a real, and this is a real component, this is your angle, and E is the internal voltage of the machine. So, already here M is called the generation inertia constant, D is the generational load damping coefficient, and delta is already I mentioned this internal bus angle with the respect to a synchronous rotating frame reference, and P g is the output, that is electrical at the generation terminal. The P m is net mechanical output, and this is normally is equal to this P g when this losses are neglected. So, this is a general I can say the swing equation. If you are ignoring this, this is normally the swing equation is used for your the classical analysis of the transient stability of machine. Now, if we are going to include, as I said, we have to go for the considering when we have to consider the flux decay dynamics as well, because once machine is loaded, there is some disturbance outside the machine, and then the flux is also going to change. So, that and due to this flux change, the induced voltage etc. is also going to change. So, that dynamics should be also accounted for, and if E q, that is the generation internal voltage behind the x d, and that is proportional to the flux field flux linkage. E q prime is the generation internal voltage behind the x d prime, and E f d if it is a generation field voltage, I d is the d axis component of armature current, V is the generator terminal voltage, and T d o prime is the generation d axis open circuit time constant. If these are the terms, then we can write the flux decay dynamics can be described by this equation, and this equation you can say this is the T d o prime, that is the time constant, d E q prime upon d t is equal to E f d minus E q. This E q etc. that can be computed, and we can feed this value can be written, this E q will be from the phasor diagram. If we know the machine characteristic, machine's phasor diagram, based on that we can compute this E q is nothing but your E q prime plus I d, the d axis current, and this is multiplied by x t minus x t d prime. Normally, this is sometimes we assume, because this is a simplification way where it is assumed this x t prime is equivalent to this x q. Again, depends upon whether your machine is your salient synchronous machine or it is cylindrical. Based on that, x t and x q should be determined. So, the T d o prime, this E q double prime, here we can write here, this is basically dot, that is some missing, you can see this E q prime. This again we can simplify in this manner, where these are basically derived from this equation, and finally, we can write this is a differential equation, that is 2. So, now you can see the equation number first, that is here I wrote here this equation number first, then we are having this equation 2. From this 2 we can see now we are having the third order model of generator, because the equation first is having the second order, and then we are adding another differential equation. So, it is a 3 order, and it is that is why it is called third order model of the generator. Sometimes we also go for the again more precise representation of synchronous generators, and that basically nothing but the fourth order model includes the additional equation, that is third, and here you can say that we are using the dynamics of the voltage generator of the d axis. So, this is the del E d prime upon d t, that term is going to be added, and this is defined as, again this can be derived by the phasor diagram and the detailed modeling of the synchronous machine. This is nothing but your is equal to minus of this x q minus x q prime multiplied by I q minus E d prime. So, the voltage equations can be written here, because all these variable here E d prime can be written here in this fashion, because we know the V d voltage, we know the x q prime, all the currents, and then we can write. Only here this the T q prime O, it is nothing but the q axis open circuit time constant, and R A is the resistance of armature per phase. So, this if you are adding this, now we are having the fourth order model. Now, even though we can also include some double primes like E d double prime and E q double prime equations, then we are going for the sixth order model as well. So, again it depends upon the need, you can go for the more detailed modeling of the synchronous machine, but normally third and the fourth order machines, as I said in the very beginning, for the practical analysis they are used for the third or fourth model of the synchronous machine. To include the air gap saturation, all those equations does not consider, as I said, that we have not, didn't consider the air gap saturation, and this can be handled by this correcting the expression the E q prime, because the E q prime, which is a q axis voltage induced voltage, when there is a knee curve we know it, and that knee curve can be saturation can be included by a saturation function this function, and this S d this function, which is a function of Portier, voltage, and that it can be written ST here, EP is equal to B, EP minus A is equal to here. A and B are the saturation constant. That can be seen here. Thus, EP is the voltage behind the Portier reactance, as I said, and the flux decay equation gets modified here because the TDO prime here, we are writing this Q prime here, this is the dot I think is missing, and this we are having here, you can say this EQ is multiplied by 1 plus some saturation factor here. So, this factor basically, this is other things are same compared to your, this is equation number 2. Here this ST, this which is a function of EP is going to be added 1 plus this, and this, that is why it is getting modified. So, the EP basically is defined, that is the Portier voltage behind the Portier reactance, it is the ED prime square plus the VQ prime square of these to be additive and the root of this. So, the XP here can be again this, the voltages can be calculated by the VD, this is the D axis voltage, here is a Q axis voltage, here minus IQ into XP, and XP is nothing but it is a Portier reactance. Now, coming back to another modeling, that is, as I said, we have to model your synchronous machine. Now, another modeling required for the transient stability is your excitation system. So, the dynamics of the excitation system, again people have gone for the various, we are using the various type of excitation system depending on the various type of generators, whether it is a small generators, large generators, hydro generators. So, we are having, again some are the old and some we are having the brushless excitation, we are having the classical excitation, we are having various type of excitation systems are used. So, the different models of excitation system consist depending upon the type of excitation basically used in the alternator. In IEEE report reference power system, this PAS apparatus and systems in 1968 and PAS 1973, 5 different standard models were suggested. These models includes type 1, type 1S, type 2 and type 3 and type 4. So, these 5 models are normally recommended and that those are normally used for the transient stability analysis. So, type 1 is a continuously acting regulator with the rotatory excitation system. In the type 1S, the controlled rectifier with the terminal potential supply only, and type 2 is your revised excitation system. This is nothing but is a brushless excitation system where saturation is the feedback is included in the feedback loop. Type 3 is the static with the terminal voltage and the current feedback, and the type 4 is the non-continuously acting excitation system. So, normally most of the people go for the type 1 type excitation system, and that gives even the better representation, even though suppose your machine is used with some other excitation system, but if you are handling, you are using one of the excitation system like type 1 or type 1S, this is giving a better picture of about your stability. But if you want a very exact, and then you have to use the what excitation system is used in that machine. So, here in this lecture only I will consider and discuss this type 1 excitation system. If you want to go for the all various excitation system, you can use any power system stability and control book, like you can use the Prabhashankar Kondur book, or you can use the Anderson and Fuad book. All they have discussed various type of excitation system, detailed modeling and their detailed differential equations, and those can be included in your transient stability program. So, in this lecture only I will be considering the type 1 excitation system, and this model has been extensively, as I said, it is used for the stability studies. Most of the people use this type 1 excitation system, and this excitation system is a consist of the measurement and the filter circuit, comparator and the amplifier, and we use the exciter, that is the DC generator here used, and the feedback compensation is used, which is the rate feedback or stabilizing transfer function, and it is stabilizes the huge changes or whatever the changes in this EFD. So, apart from above, it may also have following other basic elements, that is we should include the limiters, we should use the line drop compensation, and also we have to include the, here you can say the saturation of excitation system. In the voltage limiter, the exciter voltage ceiling, or you can say regulator voltage ceiling should be done. It should have a maximum and minimum value, because we do not want to allow this higher voltage in should go, and that may create the problem in your excitation circuits. Another is use your line drop compensation. We give another auxiliary signal in your excitation. We will see where this signal is going in this other slides. But so, before the measurement circuit to account for the line drop compensation, it is used before the measurement circuit, that is a, this is a whatever the what is the drop in the line, that is a XC, that signal is going there. So, you can say this is a signal to the measurement circuit before that. Here it is not a voltage, it is the voltage plus XC and whatever the current flowing there. So, this voltage and this quadrature of this is a modulation of this, the VC signal is used instead of the V signal. Another, as I said, we have to include this saturation effect as well, because you know, once the disturbance is there, normally in the steady state the saturation is not required because it is a steady state and it is working on the knee point, but whenever there is a disturbance, your excitation will increase or it will decrease. Once it is increasing, so saturation effect must also be taken care. So, when exciter machine is loaded, as I said, and then it voltage drop due to the an armature impedance drop and the saturation, so it is a voltage is decreasing. So, we have to take care of the saturation effect as well in our the modeling. So, these three are also used apart from the all this here I said the 4 components. Now, to include the saturation effect, already I said this is a function, that is a saturation effect, this is a B minus A upon A, and if A is the no load current to produce the rated voltage, because A is no load current, this if A is current which is producing the no load voltage, rated voltage, B is the full load voltage to produce the same voltage, the function this is defined as this. So, B minus A is equal to this. So, this function AC is the multiplier to the excitation output EFD to represent this increase in the excitation requirement because of the saturation. You can see this is a no load EFD, here this rated voltage and this is a field current. A is value here your rated voltage is A, but due to the loading the terminal voltage is going to decrease and this is your B. So, this saturation factor is defined as B minus A is equal to A. So, this factor is to be incorporated in the ERP. This is basically the multiplier to the excitation EFD taking care of the saturation. Now, I see this is the block diagram complete for this excitation type 1 excitation system, where you can see here already as I said that we are having the amplifier. You can start here this generator terminal voltage, this right hand side, this signal is coming here V, and then we are using the line drop compensator. If you do not use the line drop compensation, means this term is 0, means directly you are measuring the terminal voltage and coming here, that is a measured in your the measurement and the filter circuit. So, if you are using the line drop compensation, because some of the generators use the line drop compensator, so this voltage terminal voltage is getting modified due to the line drop and then it is used for the measurement circuit. This measurement circuit and the filter circuit, as I says, there is a measurement, there is so many harmonics, so many noises here and there, that should be the filter out, and we require the voltage here that is coming here. This voltage is compared with your the reference voltage and then finally it is going to for this your whole excitation system. Here you can see it is written other signal means sometimes we can have your generator may be having the power system stabilizer that we call PSS. Then that signal also it also give the voltage signal, and that is also used to avoid the dynamic stability of the system, and we will see the PSS, we will not see the PSS, but we will see this dynamic stability. So, to stabilize the dynamic, provide the better dynamic stability of the system, we use the PSS, and then PSS signal is also included here to take care. So, if the PSS is not there, then this signal is 0, and only we are comparing the V with the reference your V reference, and the finally this signal is there. If this is used, that is also going to be taken care. Once this signal is coming, then this signal is having the very small magnitude. So, we use the amplifier, and amplifier here you can see this is a Ka, that is the gain of the amplifier, and plus it is a time constant S into Ta, that is a time constant of this. So, this after amplifying this, we should have this some regulation maximum and minimum value, we are having the limiter, and this voltage now is coming here, and this voltage is given to your excitation system. As I said, the type 1 excitation system is a DC excitation system. So, it is a time constant and it is a transfer function, it can be modeled, and already you can see some of the books for the detailed modeling of this. We can write 1 upon Ke plus S plus Te. So, this T is the time constant of excitation system, this Ke with this parameters can be calculated, and then this output which is coming here, it is your the field voltage for your generator. So, this EFD is the field voltage which is given to the field winding of your generator, and this generator's armature terminal voltage V is coming here. So, this is the transfer function of the generator is used. You can see this EFD here is going back here, because due to the saturation effect this SE is also going to be taken care. So, some function this the EFD, as I said, the multiplier here is used, and that is getting back here. So, this will be taking care of the saturation effect. Also, to stabilize this your excitation, this should not be open loop, we are having the feedback compensation to give the better accuracy and the stability of the system. So, the EFD is coming here to the feedback compensator, and this is again going back here, and this is a compare. So, that we can maintain the terminal voltage whenever required, and this is the feedback type of system. So, this is a complete block diagram of excitation system. Wherever you can see this, there is a S, you are having S is a Laplace transform function S, and you can say wherever you are using, you are having one differential equation, one order just you are increasing in your modeling. So, here you can see 1, here you can see 1, here you are having 1, here you are having 1, and if you are modeling, you are including here. So, then you are having so many differential equations as well in your for taking care of the excitation system, and this V t is coupled with your dynamics of the first swing equation. Now, third component I said that we have to also model the speed governing system and the turbine. So, this basically I have taken from Power System Stability book, this Anderson and Ford as I said, and from there this we can have this model can be described as the T1 dx, this general expression here we can write in this fraction. Here we can write, and the various other components, other state variables x4, x5, x and the Pm, we can write the various differential equations that governing for your governing system as well as your turbine system. So, a general purpose model is given in the figure. You can see this is the figure. These are the time constant. Just I want to say this is your general purpose speed governing system, where this is your governor and pilot valve. If it is having governor system, that is a thermal power station governing system, then you are having a pilot valve if it is for your hydro. Then you are this is your speed is here, the change in the speed is coming here. Then we are having the Pm also, this mechanical output, this desired power output, that we are having the ceiling here, the limiter. Then we are having gate or steam valve. So, gate opening in case of your hydro, and the steam valve opening etc. in terms of thermal, and then finally we are going for the steam bowl where the steam here there. Then we are having the reheat, basically this is nothing but your turbine modeling. There here the reheater or the penstock for this penstock for hydro and reheater for your thermal, and finally this Pm is coming and this P electrical and this is going for the PA. So, this is a general purpose speed governing system, and you can say all the time constants here it is written that the T1 is the governor response time constant, T2 is the hydro reset or pilot valve time constant, T3 is the servo or hydro gate time constant, 0 for hydro governors basically, and T4 is the steam valve bowl time constant, and T5 is the reheater or half hydro water starting time constant, F is the soft output ahead of the reheater, and it is a -2 for hydro, and REG for your the turbine and SS regulator setting on the drop, and the P max is the maximum turbine output. So, with this we have this is a governing model, and now we have to go for this is a load modeling. So, let us start the load modeling. As I said, it is the fourth component, that the load should be also modeled accordingly depending upon the needs. In the classical, normally the loads are classical analysis of the transient stability, the loads are fixed, but if you are going for the detailed analysis of the transient stability, then you can model the load accordingly. So, loads can be classified in the three static load models. It can be three types. One can be your constant P and Q model, where the loads are independent of voltage variation, and the more generally I can say normally they are used in the load flow analysis, where the P and Q are treated as a constant. So, this is some sort of the constant P and Q model. Another is your constant current model. The constant current model, where the voltage this is a proportional, the P and Q is proportional to your voltage, and that is why it is a real and reactive power of the loads are proportional to the voltage, and the example of this is a converter loads. So, we can model this real and reactive power in terms of that is a proportional to the voltage. Third type is your constant impedance type. Especially you can see the resistance load, it is a simple resistance, and you see the power consumed by the resistor is proportional to the voltage square. So, the real and reactive power is proportional to here you can say this is not and it is a proportional. So, the P and the P, that is a real power, and Q is your reactive power, it is a proportional to the voltage square. So, taking care of all the three types of load, we can basically consider a combination of all these three varieties of load into one. So, I can write this is the real power is equal to the A naught. A naught is nothing but your the constant your P type load, and plus A1 V, which is the constant current load, that is multiplied by A1, and that is another one is your A2, and here is the V2. Here it is I think there is some mistake here, it is not V2, it is a V square basically. So, the another factor. So, it is not V2, it is should be square. So, P is equal to A naught plus A1 V plus A2 V square, and similarly the reactive power we can write say here B naught plus V1 V plus V2 V square. So, above model assumes frequency variation is negligible. So, we are not considering this what will impact on the load with respect to the frequency variation. So, ignoring this we can write this your real and reactive power can be treated as the voltage dependent, and that is you can say the constant impedance type load model. Here is a constant current, here is a constant P, and then we can combine together with the various factor A naught, A1, A2, and here similarly for the reactive power is B naught, B1 and B2. IEEE has suggested the use of following general model of load. You can see they have used here the frequency variation as well. So, you can see this P is P naught V upon V naught, and that is they are just putting some exponent, that is the PV, that is the real power voltage exponent. Similarly, they are putting this F here, that is the this is a R, it is a exponent of the frequency. If your both voltage and frequencies are varying, then you can use this model for the real power, and for your reactive power you can write the Q is equal to Q naught, and again here the V upon V naught exponent QV, and again the frequency variation. This V naught and the F naughts are your nominal voltage and the frequency, and this V is the actual voltage and the frequency, and then exponent basically depends upon the system characteristic because it depends on system to system. So, the different types of loads and as I said the quotients here PV, QF, QV and the QF are varying, and these are basically you can find in the Taylor's book of the voltage stability at the page number 33. You can find the various types of load. He has given the various components that is used. For example, already you can say for the if you are having the space heater or the resistive load, these values you can say this PV is a 2 and other components are 0. For the small motor loads, you can find these all the terms are appearing. For the large motors, you can say all the loaders without negative part here, but you can say frequency here it is a -1. So, for fluorescent lamp you can have these components, and for the room air conditioners have the following component. So, you can find for various he has computed and he found the various components can be used, but in the actual practical system it is not a single house because it is whole power system, you are having the varieties of loads. So, that is again you have to see what is the value of P and V, and there should be some normally lot of people have done for the load modeling itself, and that concept can be taken for the modeling of the load. Even though so far I discussed about the static when we were not talking about the motor loads, but you know in the power system approximately this 50 to 80% loads are your motor loads are mechanical loads, and these motor loads should have some dynamics, because some of the machines normally the loads are the induction type motor loads, and they are having some of motors are very high capacity. So, the static model have been reported to be the insufficient to capture the voltage dynamics. The major portion of this dynamic loads are the induction motor, as I said, which has the significant effect on the voltage stability and also on the transient stability. The following models of induction motors have been used by Jayed and Taleb in 1991 IEEE transaction energy conversion volume 6, and they have used, you can see here they are using this voltage with respect to time, and that is the dynamics that they have used. Here Vm is this is a voltage is the voltage behind R plus Jx. It is not less than it is the angle Vm magnitude and this motor angle terminal voltage. So, these dynamics can be used for the modeling of your machine as well, and this delta m is not a synchronous generator delta, is a machine a motor angle, and this is the rotating speed of your omega r is the speed of the induction motor. So, here the differential equations can be used for the motor loads, and some people have seen it is also affecting your especially the voltage stability. However, the transient stability their impact may be less, but that can be also included and that can be solved. So, all this you can see this terminology those were used here mm here just which we used, this is nothing but here this mm is your this m of basically the inertia of the induction machine and induction motor basically. TO is open circuit transient time constant, Xx and X primes are the steady state and the transient reactance of the induction motor. This Pm and Qm are the real and reactive power drawn at the internal node of the motor, and TL is the load torque, and that can be written as A naught plus that is a function of your speed and the rotor speed, that is omega r is basically the rotor speed. Omega s is a synchronous speed, that is omega naught plus phi s, where omega naught is the synchronous speed and phi s is the phase angle in terms of voltage which is changing. So, that can be included. Some people also gone for the different one, because they are saying the and for different models are suggested for the stability studies. The load model suggested by the Valve in the Sigre report 1986, that is if the PS and plus JQS, the real and reactive powers, are the static components and PD and QD are the dynamic components, then we can take this PS and QS as a constant, but the PD and QT who are the dynamic components, that is basically it should be added here the some gains, that is a real power with respect to the theta dynamics, and kV here the voltage dynamics. All these things are basically now added, and then people have analyzed for the transient stability. So, as said, the people are having modeling of the load is a very difficult, because in complete power system knowing at any particular instant what is the components in that load is very, very difficult. So, that is why people have taken some approximation, and from the system to system these constants should be find out, and then based on that then can be analyzed. Even the load model suggested by Dobson and Alvarado for basically in their paper the IEEE conference on the decision and control in 1992, and also by M. K. Paul in 1993 in the IEEE transaction paper, they have used another type of composite load consisting of the static as well as the dynamic components, and they have used here. This is a L is the nominal MVA demand and PF is the power factor, and then this is a D is the damping, theta dot plus A is a constant, A B are the constant. So, they have used this type of relation for the Q, they are using here the K plus V also, and that this whole the dynamics they have included for their studies. Now, coming at the last one model in the transient stability is your model of HVDC system model, and this model is taken from the P.S. Kundur book on the power system stability and control. You see this what happens, any converter HVDC link will have your rectifier at one end, inverter on one end. You can say here we are having rectifier and then we are having inverter. So, we should go for the rectifier equations, and also we should have the inverter equations, and these two are basically connected by a DC line. So, we should also model the DC line as well. In the rectifier, we know the control characteristic, that is we have the minimum firing angle control, that is minimum alpha, and also we are having the minimum margin angle, that is it should be set to avoid the commutation failure in the inverter side. But some other auxiliaries are required, because here this you require this we have to have the modulation control, and this all the signal here is you can say this side the rectifier is controlling current, however, this inverter is controlling your voltage, and this things should coming here. Sometimes also this is the reverse back, because if a power is flowing from the rectifier this end to this end, this the rectifier, now it is rectifier, this will work as a current and this will be working as the voltage, and if it is a reverse then this will work as a current controller and this will working as the voltage controller. So, you can see here the current controller both are there, and here we have the current margin. Whenever you want to change the power direction, this margin will be added here, and this current minus this will be going here, and that we will see the characteristic of the controller. Already we discussed in the module 2nd when the what will be the control characteristic of the HVDC link, and already again I will show it here in the earlier other slides later on. So, what we require, we have to calculate basically the current order, we have to calculate what should be the current, and that is basically decided by the set power, how much power you want to flow, and that power basically this is that is why it is written set power, or you can say the current. You have to either set the current or you can set the power, because the voltage you know, and then you can calculate the current. So, either P reference or the current reference are here basically there, and based on that we have to calculate the current order. To have this we are getting the signal from the rectifier side, the AC signal, and also from the inverter side AC signal, and these signals are used to have the modulation control, and that signal is coming here, and based on that difference we are calculating this current order computation. This is a master control, and here you can say we are measuring the DC voltage, because here the power is coming, then you have to measure the voltage and then you can calculate the current. Now, this side you can see here the blocking and unblocking signals are also used, because sometimes you have to block the rectifier, sometimes even you can say bypass the signals also we use, sometimes some of the bypassing signals are used, especially when the starting and stopping, or there is some fault in some of the valves, then it should be also bypassed. So, these are the auxiliary signals are also they are sometimes given, and then after that if the DC scheduled voltage, this what is you require, what you are measuring. Based on that, we are calculating the DC voltage. So, these signals are basically during the starting, stopping, or you can say there is some fault and other things we can go for the bypassing this. So, this you can see this voltage is coming to the inverter side. So, in the normal fashion, if the power is flowing from this rectifier to the inverter side, this rectifier we require the current signal here, we require the voltage signal. But as I said, whenever we may also require that this inverter should operate in the constant current mode, and then we have to bypass, change it, and with along with some change in the current margin. Already I discussed these things, how this is changing, and in our module number 2 when the controllers of HVDC link were defined. So, then this inverter equation, and after that we are having the inverter AC injection buses where they are connected to the AC side. Here they are coming again the rectifier AC side where the AC system is there. So, already we saw the various modeling of the AC side components, and now we have to model all these controllers here for your the DC, and this should be included. So, to see this converter and the line equations, we have to go for the modeling of the lines. Sometimes we take only the resistance, we ignore the capacitance, etc. But if you are going for the detailed modeling, you have to also include the capacitance between the two poles. So, in the control, we know there is a 3 type of control. This is a control characteristic which was discussed in the previous module. Here you can say this is AB is a alpha minimum control, and that is called here this is a CIEEE control, that is a constant ignition angle control of the rectifier side. This BC part is a constant current. You can say this is a current axis, this is a voltage axis. So, this is a constant. So, the constant. So, in the normal operation you can see here the constant rectifier is working on the constant current CC, that is a constant current control mode, and the inverter is working on the constant extinction angle control CEA control, and this is your basically this curve is basically your CEA control, and the intersection of these two characteristics CC and CEA is your actual operating point. But due to the change in the voltage or the limiting or the problems in the AC and DC sides, because suppose there is a huge voltage drop and your OLTC etc. is exhausted, then your characteristic can shift. So, then we have given another characteristic. You can see this your rectifier is working here because this here, and your inverter is working your constant current controller, because this voltage can be falling here, and you can say various characteristic we can get, and this normally here, and this intersecting somewhere in this axis FG. There is also possibility that we are operating here, and then this zone F here, this characteristic is given, that is called constant beta control, and already I explained why we are going for all this control. So, this characteristic was completely defined, and I have taken again back from the module 2 when the control characteristics were defined basically. So, this characteristic is again we are having the various modes of control, and this we have to incorporate in this. So, here as I already explained the various modes of converter control, and it should be represented by appropriate dynamic models, and we will see later on in this section. Another is the line equations, and the line equations basically it is nothing but the DC lines, where this dynamic model which represents the resistance, inductance and the capacitance effect of the DC line can be included. The capacitive effect may be very important, especially if you are having the cables, and then it should be properly modeled. So, in this converter control characteristic, first characteristic as I said it is the CC control, and you can see the constant current controller here is represented in this block diagram, where this ID here the modulation current is compared, and then we are having a switch which is either closed at this point or closed at O, and then we are having this transfer function, and finally, the T3 is the response type of the current loop, and we are having some limiter here because current should not exceed certain values. So, the limiters are used, and this is your integrator 1 upon S, and then finally, we are having either D desired restart or is to S2, and then we are finally getting the ID current. So, S1 is the switch to O here, this S1 if your E is less than E desired value, and then it can be calculated. This S2 here is the switch to O if line has to shut off, then we have to the node DC current here, this should go somewhere here, and the DC should be restarted. So, this is that one. Another we are going for this complete, you can say this converter control, and this converter control basically this detailed, this is a SVDC converter model that you can see here. This block diagram is taken from the book Power System Stability and Control by the Prabhashankar Control. Here you can see the VD which is measured, and this is a transducer where we are measuring the DC voltage. This DC voltage is coming here, and then here this is a for the inverter we will see the later on what is the 4 is the P desired, thus we are value are getting, and then we are coming here. We are also measuring the current here. This current is the DC current, and then we are using the DC transducer, and it has some time constant. So, the current is coming here, and after this current here you are measuring, and the voltage you are measuring, then this plus line resistance RL, if you are adding here, then you are getting the actual voltage of your, you can say, another side, that is you are going for the inverter side. If you are measuring the voltage of your inverter side here, because we are measuring the inverter side, and then the current is there, then we can calculate what will be the voltage on your rectifier side. So, this voltage is this, you can say this voltage multiplied by this circuits, we are having this V. So, after this V, we can calculate if you are having some P desired value, and this P desired value divided by voltage, you are going to get the I desired, and this is the constant power mode in this way. So, you can have the two types of controller here. You can see I desired, either you are having the constant power mode, or you are having the constant current mode. If you are having the constant power mode here, P desired, then I desired is calculated accordingly, or if this switch is here, then you are having the constant current desired mode, and this is coming value here. From here, basically we have to see this voltage, this current should not exceed. So, we have to determine the maximum current, that if it is having some limiter, and this max is basically used here, I ordinary is equal to I dash, and if I minimum is between this I ordinary, we have to set this ordinary should not go so that limiter. So, I ordinary here, that is a determined, that is the current order, basically its order, I order is calculated here, and that coming here after the measurement we are dividing this value, and then we are having this current regulator. You can see here the Ix is nothing but the, which it is written C1 is nothing but Ix is I reference my I modulation for the rectifier, and the Ix is equal to I margin for the inverter. So, here we are using some is addition. If it is an inverter, then some margin is added. If it is an inverter, then the reference minus your the modulation is going to be added here, and then based on that we are calculating the current regulator, and we have the limiters, means this current should not exceed very high value. Then based on that what we are getting here, we are getting the compensated current control voltage, and that voltage is basically added with this whatever the ID you are measuring here, this is multiplied by 2 RC, and this is the voltage, the commutation voltage you are getting. So, this voltage and this voltage both are added, and then this is known as the IV alpha, which will decide your the what will be the value of alpha. Here also while calculating this alpha in the delay angle computer, here we will see this value should not exceed maximum and minimum value due to the various regions, and then based on that we are getting the constant alpha, and this alpha basically coming here. You can say the commutation voltage is also here from calculated, the commutation voltage transducer it is measuring, and this is going to be added, which is used to calculate cos alpha. If you see the basic equations of a rectifier circuit or inverter circuit, we are using the voltage cos alpha Vd, some voltage multiplied by the cos alpha, and then another component is coming with the commutation reactance multiplied by the current, or you can say commutation voltage. So, that is used to calculate this cos alpha. So, this alpha is to be calculated. So, in this is complete, you can say whether you are having your converter is your working as a inverter mode or it is working your rectifier mode. This complete block diagram is used for both. Only we have to see where it is inverter or rectifier. Based on that the modes, as I said, the either it is a CC modes, already these modes which I explained, which one is working on which mode, whether inverter is working on the CC or beta or CA, it can work in the 3 modes. This can work in the 2 modes, that is a CC or CIA mode. Based on that we have to already we have to write the here the switches and etc. will be formed, and then we have to write the differential equation accordingly. So, along with the other equations here you can say some of the values which are defined here is the 2 is the gamma, that we are using gamma naught, that will be used in the differential equations here, and also P desired is the specified at the rectifier end to determine this current for the inverter, and the voltage drop due to the line drop is to be taken into the account. This is a I here, this order is to be calculated. Now, we saw all the modelings, and modeling include your each and every component. I said including your AC system, that is including the synchronous machine, excitation system, governor system. Then we have to go for the load modeling, and the final just we have to include your HVDC system. If you are having some other controllers like your static wire compensators or TCSCs or UPFC, I can say if you are having the flexible AC transmission system devices controllers, that controller should also be modeled and then it should be added. So, as all the controllers along with the machines should be included, and then you have to write the governing equations, and those governing equations are your the differential equations along with the network equations, and this should be solved. So, to sum up the conditions, basically what are the worst case, what are the faults normally are considered. Already we have seen the faults in the AC systems, we very well know the various types of fault. It may be your 3-phase fault, it may be your line to line fault, maybe single line to ground faults. All the faults are basically analyzed, and we see what are the critical faults, those where the system can be unstable. So, similarly, there are the various faults near to the HVDC system or inside the DC system that should be taken care. Already the mal operation and other things already I have discussed in our previous modules. Here we can consider the various worst case disturbances for the planning and operating criteria, and those are basically, if you will see the DC side, we have to include the bipolar outages with the no restart, or we are with unsuccessful restart of the both poles. If the both poles are out, or we are trying to close and still it is not working. So, that event is the DC side we are taking care. We can also take if the fault is occurring in the DC line along with the resistance, and because we are having some capacitances, what will be the dynamics, what will be the current level, etc., that can be also seen. On the rectifier side, we can go for the single line to ground fault and the AC, that is AC fault with the breaker and the pole outage. If the fault has occurred at the converter station itself, and then the breaker and your then pole is going to out, then what will be the repercussion in the whole system. We can similarly, this is as I said, the single line to ground fault is a not very severe fault compared to the 3-phase fault, but the 3-phase AC fault at the critical locations near the rectifier should also be seen, and the impact should be analyzed properly. Similarly, we can also analyze for the faults related to the inverter side, and inverter side you know the faults are very, very severe compared to the rectifier side, because there is a possibility of the commutation failure and other things in the inverter station. So, we have to go for the various faults here. Instead of inverter side, I have to write the instead of rectifier side, I have to write here the inverter side, and similarly here also here at the rectifier we can write the inverter. So, some other faults, like even though there is no fault and there is some delay in the signal in the, you can say, the firing circuit, that may be leading to the commutation failure, that should be also taken care. So, all these things are basically analyzed in this whole analysis, and then complete AC DC system should be modeled, and then we have to solve these all the differential equations, and then we require some tool to solve, and that we will discuss in this next lecture. But to summarize here in this lecture, I can say that in this lecture we modeled and we saw the various level of modeling of synchronous machine. We saw the third already in the previous lectures we have seen this swing equation, that is a second order. Then we say the flux decay model, we use the third order, and we also saw some other models like the fourth order models also taking care of saturation. Then we saw the type 1 excitation system having complete block diagram, complete modules, complete blocks of that, including your amplifier, line drop compensation, excitation system models, measurement circuit and saturation effect, etc., is taken care. Then we have to go for the governor, and the turbine models are to be done for all your hydro as well as the thermal power stations, and your load model is also equally important for complete transient stability. So, people can go up to certain approximation of the load model. As I said, it is a very difficult task to model the load, because complete power system having the varieties of loads and it is keep on changing. So, it is not a fix. So, that is we have to go up to certain level of the modeling of the load as well. Maybe it is the voltage varied load or also frequency dependent, and moreover we have to also take some dynamics load. And in this AC/DC transient stability program, the modeling of the DC, that is HVDC converters, its control aspect and the DC lines are also very important. So, already in the previous lecture I discussed that we can go for the 3 level of model. Simple model, that is a very simple, where almost HVDC line is excluded with simple say injections of real and reactive power. then we can go for the response model, and then finally it is a detailed model. So, if you are going for the detailed model, I can say that you have to model all these aspects of the converter as well as the DC lines and their control modes, along with some various other small operations should be included, and that is we have to model, and then finally we have to write the governing equations along with some algebraic network equations, and that should be solved. Thank you.